So, all right, we are on time. Let's start. Right, it's 3:30. So last time we briefly discussed how we should think about overall phase and amplitude of the reflections, right? Okay. Today we'll go in a little bit more depth of what range and resolution and how we should think about those. Okay. Everybody can see my screen, hear me clearly on audio. Just say yes if
Yeah.
anyone on the sounds good. Okay. All right. So again, join Piazza, right? Okay. As everyone, right? Today's outline of the lecture will be, we'll start where we left off on the phase, and we'll understand how from that phase, how does range, resolution, and all these things play into the matter, right? And what should be the wavelength, right? To meet both the requirements of the breathing and heart rate, which is 10 centimeter to zero point 0.4 millimeter, or let's say something around that idea, right? And similarly, we'll also go over the uh, aliasing part, right, and the resolution component, right? Okay. And similarly, we'll look into how we should think of general FFTs, their range and resolution. And this is what I found something, it seemed a little bit of concept somebody didn't get well, right? Or most people don't get well even after taking classes on DSPs and whatnot, right? So we'll just briefly cover it, right? So that just refresh your concepts on that front, right? Okay. And then basically we'll use this, right, to look at how to generalize it to multiple wavelengths. Okay. All right. So let's go over the simple architecture, right? Okay. What is our architecture so far has been? Our architecture has been that we have transmitter, right? Okay. It's transmitting one sinusoid here. Okay. Right. Okay. At center frequency FC. Okay. Right. In the same transmitter, right? Okay, you just essentially use the same received signal, right? And I think please don't think right now and confuse yourself with down conversion and so on and so forth, right? Assume for now we are just receiving at the passband frequencies, right? Or at just directly receiving the data, okay, right? Okay. So what I mean to say is that we have a receiver, right? Okay, and we are receiving the data, okay, at these different values, right? Okay, and essentially we are getting the reflection back from the human body, right? Let's say this is person, right? Okay, and it has heart rate and breathing, okay, right? Not the greatest figure, but basically you get the point, right? And really we are receiving this signal and we kind of try to get sample this signal at different points, right? Okay, essentially like as Ish discussed, right? Um, yes, and basically that kind of gives you what kind of phase and all those things you need to measure. Okay, right. So now going forward, right? I think just to recap, right? In this discussion, we are just assuming previously that we'll get immediately the phase on the receiver side, okay, or amplitude A hat of T, okay, right, okay. And we went on to the discussion of basically understanding. Sorry, are you? Sorry. Let me just write as pH, okay, and we can, if I write phi, then just assume that that's the basically the phi hat of phi, okay. And what we discussed last time is following, right? Okay, this is basically getting your alpha h squares phase and amplitude for the same thing, okay, right? Okay, right. Now, as we discussed, h square essentially is nothing but, recall, exponent of minus j2 pi d over lambda, or 2d over lambda, right? Because d on one side, d on the other side, right? I think there is a lag I see here in this slide, so I will try to also slow down in that front. So basically, this is how we get this 2d over lambda, right? And as we noted, d is a function of d of t, right? And d of t is nothing but d0 plus db into sine of 2 pi fph FPT plus DH into sine of 2 pi FHT. Okay, right? So now that's said, right? Okay, we have phase measurements, right, from this 0 to 2 pi, right, as we discussed last time, right? Okay, so basically the phase, and let me just sort of change a little bit of this variable so that we don't confuse ourselves, right? I want to change this variable. Sorry, did I not erase? Huh. I don't know why it's not erasing. Okay. Anyone has a suggestion on what's going on? Why isn't it erasing? Anyways, I think I'm just gonna overwrite on this. This is going to be called as phi, okay, right? So that we all have an understanding, right? And remember, phi is measuring this 2 pi 2d over lambda, its phase, right? With the modulo of 2 pi, okay? So what I mean by modulo of 2 pi is that from 0 to lambda by 2, it just essentially gets the phase value from 0 to 2 pi. And beyond that, right, any value will keep wrapping around, okay? The great part about wrapping around is that basically on x-axis here is distance, okay, right? So what is our, like, let's start with the very simplistic thought process, right? What is a simple thought process, right? My simple thought process is this, right? I want to make sure that the breathing, right, okay, and heart rate, right, okay, are confined to one cycle here, okay, right, okay. Everyone clear on why I want to confine that to one cycle? So that just looks like very much, there is no aliasing effect, right? Okay, what I mean by aliasing, right? Let's now think about aliasing. What happens really is following. Let's say if I measure a value of phase phi here, okay? I'm going to change my pencil color so that it's clear, right? Let's say if I'm going to measure a phase value phi here on the left side, everyone can see this, right? Okay, what it means is that I can be at distance this, right? Okay, everyone follow? These all possible distances can be solutions, right? Okay, so really, what am I saying? I don't know the distance. Okay, what I know is that distance can be, let's call this as alpha, right? Okay, it can be anything plus alpha plus lambda by 2, alpha plus 2 times lambda by 2, right? Which is basically this point right here, okay? And then this point is alpha plus lambda by 2, and this point here is just alpha, right? Okay. So really, what is our aliasing? Our aliasing is lambda by 2 factor, okay? Anything above or below with lambda by 2, we cannot say for sure, okay? All right. Everyone with me on this? Now, let's take an example, right? What is breathing? Okay, breathing's amplitude, right? Okay, or rather distance. Breathing distance, right, is equivalent to somewhere between 10 centimeters. Okay, right? Okay. So what we are saying is that if we can capture this entire wavelength here, okay, right, of breathing into one wave, that would be ideal for us. Okay, all right. So we are going to confine lambda by 2 should be less than 10 centimeters. Okay, right. Okay. Everyone clear on this part? Please feel free to ask question as to why I'm doing this. Right. I just want to confine entire breathing into one cycle. Okay, one cycle here. Okay, right. And as we saw that aliasing is of lambda by 2. Right. Okay. Now, can somebody tell me what is the resolution of this, right? Okay, what is the minimum we want? The minimum is heart rate, right? Okay, right? Okay, and this is somewhere between, let's say, zero point 0.4 millimeter. Okay, what does that mean to have zero point 0.4 millimeter resolution, right? Can anyone tell me what it really would mean here? What it would mean rather is that what should it be accurate? What should be accurate? The phase accuracy, okay, right, should be less than this zero point 0.4 millimeter equivalent, okay, right? Tell me what this means, guys, to me, okay? So let's say lambda is equal to 20 centimeter, okay, all right, less than 20 centimeter. This implies this, okay, right? So let's take lambda of 20 centimeter, right? Can somebody tell me what lambda of 20 centimeter mean in the frequency, FC? So FC will be, what will be FC, guys? 1.5 gigahertz, okay? So the way to think about this is following, okay? It completes one wave in 20 centimeter, okay? And if generally with the speed of light, right? Lambda equals to 30 centimeter implies 1 gigahertz, okay? Because 1 nanosecond can travel 1 feet or 30 centimeter or whatever, however you want to interpret, right? Okay. So this turns out, and you can do the calculation, that turns out FC is 1.5 gigahertz, okay? Now, how do I connect this with this, okay? What is the idea, folks, here? Anyone? Thoughts? Why don't we type on chat whatever thoughts you have or just speak out? So what it means is really, right, I need to get some bits of resolution, okay? Let me erase this part a little bit, right? Okay. I need resolution here, right? Okay. Of, let's say, 0.2 millimeter. Just to capture 0.4 millimeter, I need resolution, at least 1 bit resolution of 0.2 millimeter, okay? What does it mean? What it really means is that the phi you're measuring here, right? Okay, okay, the accuracy of phi, correct? Everyone follows this? Please say no if that's not something which is making sense to you, okay? I'm gonna call out people. Puneet, does it make sense? If you can unmute and speak out, that will
Yes,
be great.
yes.
So what I'm saying is that in order to meet this 0.4 and have at least some resolution for this, okay, right? Dylan, following me?
Yeah, I'm following you.
Okay, great. Okay, so zero point 0.4 millimeter, right? Okay, would ideally make it for plus, let's say plus minus 0.2 millimeter, right? Okay, is the resolution I want, right? 0.2 millimeter will be how many degrees in phase? So let's do a calculation. So what we understood is 10 centimeter is equal to 2 pi, okay, right? What is 0.2 millimeter in that case? It's 2 pi into 0.2 10 power minus 1 for centimeter, right? Okay, divide by 10 centimeter, okay, right? So it's essentially 2 pi into zero point 0.2 into 10 power minus 2, okay, right? To be clear, right, this is radians, right? So we can convert this into degrees, right? It's rather saying that I need to have 360 times 0.002 degree accuracy, okay? Everyone with me? This is equal to 0.72 degrees, okay? Everyone following?
Yes.
Okay, good. So I have resolution, right? Okay. So let's revise now, okay? I have phase accuracy needed, okay? I have wavelength, right? Okay. right? Okay, 20 centimeter, 0.72 degrees, right? Okay, and what else I have? Sampling rate. Okay, what is the sampling rate, folks? As we discussed, right? It could be how much can be sampling rate, folks, from last meeting, last class. It can be,
I think it was
so
three hertz.
yes, at least greater than 3 hertz, and we use 60 hertz in the last discussion, right? Okay, right? Okay, but it needs to be greater than anything greater than 3 hertz. Okay, right? So now all of this, right? How do we put this all in context? Okay, right? Like, does like how do I really go back to this figure here? Okay, okay, and really understand how to like really design the system. Okay, right? Everyone with me?
Yeah.
Sorry, I heard maybe a little bit. Is that someone who has a little bit or some questions? Eric, how about you?
I'm doing good so far.
You're good so far?
Yeah.
So if you guys have a good background on signal processing and whatnot, then maybe if you want, like this lecture, you can probably watch later in the video as well, up to you, okay? But I just want to make sure that everyone in the class, both undergraduates and graduates following me really well, okay? So just let's write down and draw the simple system out, okay? So I have a transmitter, okay, which is using center frequency FC of 1.5 gigahertz, okay, right? Okay, and it's transmitting this tone, okay, right? Okay, and receiver is synchronized with this transmitter, okay, right? Okay, what it means is that it knows time t equals to 0 is same on both transmitter and receiver, right? That's very important, okay? And let's say this is the distance of d which is traveled by this sinusoid, right? And it comes back here, okay? So this sinusoid, then let's say in order to process it, right? Okay, I need to sample it, okay? All right, okay, right? So first thing, let's say the signal here input is 1.5 gigahertz, right? What is the difference in the signal received here? Puneet, what is the difference in the signal which we receive here?
And the phase difference and then
So basically, the signal will arrive first at distance of 2d over lambda, or time after 2d over lambda. Okay, right? Okay, right. And this wave then will have an additional phase. Okay. Now, what is really happening truly in physical world? Physical world, what's really happening is that this d is changing a little bit here and there, right? Okay. And what that really means for this sinusoid is that it's getting a little bit of stretched sometimes, okay, right? And sometimes it's getting squeezed, okay, right? It's like the Doppler effect, okay, right? Doppler is causing this process to stretch and trim, okay? Sorry, other way around, okay? Everyone with me? But it's the stretch is very small, very minimal stretch, okay? And what I mean by minimal stretch is that, imagine, right, I'm trying to measure breathing which is somewhere between 2/3 hertz, okay, less than 2/3 hertz if I remember the numbers correctly, and heart rate which is somewhere between 1 hertz, okay, right? Okay, sorry, let me write it more cleanly, okay? So basically, I'm trying to observe things which are between 0 to, let's say, 2 hertz, or best case 1.5 hertz. Okay, right? Okay, right? And more or less, right, what that leads to, right, is that I need to measure this for so long to measure small differences of 1.5 hertz and whatnot. Okay. Remember the length of n. Okay. All right. So let's first do following. Okay. The signal here at the input of the ADC. Okay. Right. Is 1.5 gigahertz, right? And from the lab, you guys all learned, right, already now. Let's say if you have a signal which is analog of this much, right? Okay. You should sample at least twice the sampling rate, right, guys? Okay. 3 gigahertz. Okay. Right. And I think some people may have a better idea of on how to sample it, but let's continue with this 3 gigahertz idea for today's class. Later on, I will tell you how to optimize this further down. Okay. All right. So, and you basically get the same sinusoid with different samples. Okay. Right. Okay. But you get samples for this, right? So let me just draw it with a different color here. So basically what am I doing is that if you take this x-axis of here, right, this received signal, after ADC, right, okay, what happens is that I get samples of this thing, right, okay. Like it should be like 2 samples per wave. I'm drawing more samples, let's say here, okay, right. And I'm getting these samples, right, like what you saw in the lab, right, is showing you in the lab, right. And Ish, please stop me if you haven't done it, right, and if there is something incorrect here, okay. Right. So everyone get it that I got these samples, right? Okay. Now here comes a question, right? Okay, Dinesh. You told us about this, right? This wavelength you have followed, right? The sample rate, how does this gets implied and implemented here, right? And how does this accuracy come into the play, Dinesh? Okay. Right. Can anyone wanna take a guess on this? How to go about doing this? Because look, I'm getting 3 giga samples right now. Okay. 3 gigahertz, one sample almost every so fast, right? Any ideas, guys? How do we go about that? How do we start thinking about the phase accuracy and the sampling rate of just 60 hertz here? You're getting 3 gigahertz, right? How do you go to 60 hertz now?
Does it have to do with doing a down conversion from the carrier frequency?
Not well, in some sense, yes and no, right? It's more to do with averaging. Okay, all right. Okay, so now, right, let's write down this signal. Okay, right. Okay, this signal is basically after ADC, right? Exponent of J2 pi FC, right? Sorry, let me first write down the mathematical model of the signals before. Okay, so your transmit signal x of t, right, is exponent of J2 pi FCT. Okay, right. Okay, the received signal will be xt minus tau. Okay, or here tau is nothing but 2d over lambda, right? It's the time it took for it to travel 2d distance. Okay, so this will be exponent of J2 pi FC t minus tau. Okay, right, with a hat as amplitude. Okay, right. Okay, and this is nothing but your received signal. Okay, everyone with me on this so far? Confused with the notation? This is your received signal. Okay, Eric, following?
Yes.
Okay, fantastic. So now with this received signal, right? Okay, our goal really now is to, what we do is we essentially take Y and we sample it at NTS points. Okay, right? Okay, so we essentially took exponent of this, right? I'm going to assume A hat to be constant a little bit for now. Okay, J2 pi FC NTS minus tau. Okay, right? I'm just going to call NTS, just drop TS notation for now a little bit. Okay, or let's keep it for now, maybe. Okay, let's see. Let me rewrite this expression now. Exponent of J2 pi FC N ts, right, times exponent of minus j2 pi fc tau. Okay. What is this? We discussed this in the last class. This is exponent of minus j2 pi 2d over lambda, right? Everyone with me? Dylan? Following Dylan? If you can say yes or type yes in the chat, that either would work for me.
How are you canceling SC there?
Sorry?
How are you canceling out SC in your second term?
FC in tau here, I can do that. I can do the simple math. Is that what is unclear right now, Dylan?
Well, just the equation above, you define tau as 2d over lambda.
Oh, sorry, that was wrong. My bad. Sorry. I see. You're correct. Thank you. Thank you for that correction. This is 2d over c. Sorry. Speed of light and total distance traveled. Okay. So let's do this quick calculation. FC into 2d over. Thank you, Dylan, for that correction. Okay. C, right? Okay. And c over FC is nothing but this. Everyone with me on this? Dylan, you following?
Yeah, makes sense.
Yep. Thank you for that correction. Appreciate it. Okay. And guys, everyone be attentive. Okay. It's easy to make some of these mistakes easily. Okay. All right. So now look at this, right? This is the received signal I have. Okay. Right. Okay. Now this part is a standard part. Okay. Right. So this is the part which I'm looking for. Okay. Correct. Everyone with me? This is like the constant, right? It's the same thing, right? Okay. What can I do here, right? What I can do is I can take y of nts and multiply it with exponent of plus j2 pi fc nts. Okay. Right. Okay. And that gives me following: a hat exponent of j2 pi 2d over lambda. Now let me write this d as d of t, function of time. Okay. Everyone with me? Anyone has doubt about this expression? Any questions as to how do you know FC, how do you know NTS, right? This is because basically FC is given to me because transmitter and receiver are synchronized. NTS because time is synchronized at the transmitter and receiver both are the same, right? Okay. Everyone with me on this? Dylan? How about Eric this time for you? Eric, good.
Yeah, I'm following.
Okay, fantastic, right? Now, even then, right, all of this is coming at gigasample, okay, 3 gigasample. More importantly, let's write this as following: a hat exponent of minus j2 pi d of nts, okay, because t is ts at this point, okay, right? Still with me? I just replace t with nts, okay. Okay. So what I'm gonna do is now, how do I go to 60 hertz with accuracy of 0.7 degree? Right? Ideas? Have you heard of averaging? Everyone with me? Puneet.
Yes. There shouldn't be a negative sign in the formula, right? For the
Which one?
if you go one more step, the tau, when we replace the tau, t minus tau, right? So when we did the sampling,
Sure, that's a good point. Everyone following what he's saying? It should be positive, or let me actually correct it differently rather. Okay. So I will do corrections. Okay. I think, Puneet, thank you for pointing that out. I think the notation was correct to start with, rather. Let's start with transmitted signal as positive exponent of J2 pi FCT. The received signal, then there should be this, right? Okay. T minus tau, right? And therefore this should be this, right? Okay. This should be this should be this, right? And therefore this should be multiplied by, folks, don't worry about this. This is just a notational thing. Okay. Thank you for correcting it. But this then will be, okay, this is then correct. Okay. After that, this part is correct. Okay. It still has to be negative. Okay. Everyone clear? Eric, Dylan, questions? I think I'm just taking a pause so that everybody is clear here. Okay. Now, Puneet, do you want to, Dylan, go ahead. Yeah, you're saying?
Yeah, everything's clear. I'm just kind of stumped on the 60 hertz and 0.7 degree accuracy.
Well,
I'm just kind of stuck on the 0.7 degree accuracy.
okay, all right, that's fine. I think that's why I'm here, right? Okay, let's go over that now. Okay, so what is the simplest trick you guys can do? Okay, so let's just draw this in time domain. Okay, so after multiplying by the negative exponent, okay, all right, what would happen? Okay, so if you think about it, right? Okay, let's draw a picture now. Okay, so this is your signal. Okay, I'm drawing it as a continuous. Okay, but just think that this is your FC times T signal. Okay, right? Okay, and these are the samples you will be capturing. Okay, right? What happens with the received signal, right? Okay, this is this part of the signal is what I'm drawing here. Okay, okay, all right. Now let me draw Y of T as well. Okay, so this is your sorry, hold on. Okay, negative FC of NTS. Okay, now exponent of that. Okay, right? Okay. Now, similarly, what I have here is now basically, if this is negative, right? The YT minus tau or YT, signal YT, will be something like this. Okay. One, it would start, let's say, with a delay of this or somewhere between here. Okay. Okay. Now, this. So I'm just trying to make sure I don't draw it wrong. Okay, let me just draw it right. Okay. So the frequency don't change that much. Okay, it's very slow change in frequency. Okay. So essentially, let's say, oh, the wave starts here. Okay. Now, what is the difference between negative FC and positive FC, guys? Anyone want to say?
It's just the direction you're going. So if it's positive as you transmit, when it reflects and comes back at you, it's going to be negative.
Sure. So I think it's rather to say the power in I and Q. Okay. Right. Okay. Keep shifting back and forth. Okay. All right. So the point is, after you multiply this and this, right? Okay, what you're left with is this particular component. Okay, right, which is like a slow changing phase. Okay, right. Imagine a 3 giga sample, right? Okay, at the time, like from one sample at 60 hertz to the next sample in 60 hertz, right? Okay. How many samples do they exist for 3 gigahertz, right? You almost always have, let's say, somewhere between, so 3 divided by 60 or hertz, right? Okay. So essentially you have somewhere between 3 divided by 60 is 1 over 20, which is 0.05, somewhere between
500.
500 million samples, right? Correct? Okay. So does, I think this might be somewhere around that. Okay. I think you guys can correct this calculation. But more importantly, you have 500 million samples between the 260 hertz sample. Okay. So really, the idea is very simply following, and this is what you do. Basically, you multiply these two, right? And what you get is really a constant phase thing, and whose phase is not changing between these two samples, okay? Or very, very same, okay? So what you do is really you do some kind of you take all these samples, right? Okay. And you average them and call it out as this particular sample's phase value, okay? Right? Now, let's now understand, everyone clear on how to get 60 hertz sampling rate? Eric?
Yeah.
Yeah. It's just very simply stating just a simple multiplication and then averaging to get to this one sample. Okay, right? Okay. And then the same thing for getting this sample, you can do averaging from here to here. Okay. So now just to rewrite this, right? Okay. Let's say I have these 500 million samples. Okay. And by the way, somebody should check my math calculation here. Okay. From this point to this point, right? You have 500 million samples. Okay. Then from this point to this point, you have another 500 million samples. Okay. These are 60 hertz points. Okay. Okay. Right. So what you can do is you can just even average samples from here to here, samples from here to here, right? Okay. To call out sample at 0, sample at 1 over 60, sample at 2 over 60, right? Okay. So these samples you get, right? Okay. And when you take their phase values, okay, that's when you get this part. Okay. Everyone with me? That's when we get this part. Let me highlight this part rather instead of this part. Okay. With all of this magicness. Okay. So you get this part basically. Okay. After averaging, and it has a hat as well. Okay. All right. Everyone with me so far?
Yeah.
Okay. So now let me ask different questions here. Okay. What is the accuracy? Renji, you had a question? Sorry, you unmuted yourself. Please go ahead and ask yourself. Yeah, go ahead.
No, I just respond yes.
Okay.
Can you hear me?
Yeah, I can hear you.
Oh, okay, cool.
So I get y of at 0, right? Y at 1 over 60. Okay. I'm just writing these time in absolute scale so that you guys understand this part better. Okay. Y 2 over 60, right? Okay. Everyone clear how I'm writing y 1 over 60? Eric, Dylan?
Yeah.
Okay, good. So I have one sample. Each of them has a value of a hat and exponent value, which has j2 pi, some 2d over lambda, and d at 0. Okay, right? Same thing here, right? This value here, okay, is a hat exponent of minus j2 pi d of 1 over 60 upon 2d over 1 over 60 upon lambda, right? Okay. Everyone following this notation? Okay. It's clear enough, right? I can rewrite it quickly, but it's fine. But basically we get the point, right? We get these samples, right? Okay. Now tell me what is the accuracy, right? Before you tell me accuracy, right? I need to give you some knowledge, right? Or some specification, right? Specifically how accurate this ADC is, okay? Right? And there are like different distortions people carry, okay? Right? And they are relating to phase noise and whatnot, okay? Let me simplify ADC specifications, right? Okay. So ADCs, right? Again, this class is not about ADCs. You guys can take ADCs and understand it better, right? But let's say ADCs can cause an error of 6 degree, okay, right? While they are sampling at 3 gigahertz, okay, right? So does everyone clear on what the 6 degree error means? So what it means is that instead of measuring E exponent of j phi, it can measure exponent of j phi with plus minus 3 degree error, okay? Again, convert this into radian, okay? This is 3 degree error, okay? Right? Eric, Dylan with me, and who else is here other than you guys? Okay, yeah. Everyone with me on this? Eric?
Yeah.
Sorry for on so much on you guys, okay? But yeah, so now can someone tell me what is the performance, what is the error in Y0's performance after averaging? Did everybody get the question? So let's just write down following, okay? What am I doing? I'm mathematically speaking, right? I'm basically taking this expression here, okay? Okay. So I just took this expression from the previous slides. Okay, everybody can see this expression. This was the expression we essentially drew upon here. Okay, right? This was the expression, right? Which has constant amplitude and this phase thing, right? Okay, right? And we are averaging this, right? Okay. So what is this math saying here really? Okay. So what are we doing? In mathematically, we are doing following. We are averaging this for n going from 0 to, let's say n goes from 1 over 60 up to, okay, right? Or rather, let's write it this way, okay, that y of 0 is basically n going from uh, some minus 250 million, okay, to plus 250 million, okay, right? And where TS is nothing but 3 giga samples per second, okay, right? Or 1 over 3 giga samples, okay? Everyone with me on this expression? This is how the formulation of Y0 comes into play, right? Like, remember this averaging we did from minus 250 million to 250 million, right? Okay. Dylan and Eric following?
Yeah, I'm
Yeah.
following.
Puneet?
Yes, I'm following.
So what really we are saying is that each of these terms, right, has, let's call it, let's say underlying observation was y hat, okay, but we made a noisy observation, okay, each of them is noisy, okay, it's y hat plus n, okay, and n really can cause error of 6 degrees, okay, right, okay, and you can write down n's error in amplitude as well, okay. So what I'm trying to point is following. Each sample has this much error, right? By doing this kind of averaging, you're averaging y hat and noise, okay? And you're dividing this by 1 over 500 million, for example, if you're doing averaging, right? Okay. So you're dividing this by with 500 million observations such, okay, right? Okay. This gives me, again, everyone with me? And each of them is an independent noise, okay? Ni, okay? Right? Everyone with me on this? Eric?
Yeah.
Okay. So basically, once you average all this scaling, right, and assuming that your received signal has amplitude of plus minus 1, right, okay, with an error of this, right, okay, and if you start doing such kind of averaging, right, your accuracy will get to how much? Anyone want to take a guess? You essentially have error of e power j plus minus 3 degree, and your variance will go down by 1 over 500 million of that, okay? Okay. Everyone clear on this particular observation? The only point I want to rather make is that this will kind of, you can do this division, right? Okay. And it kind of goes into a little bit of probability of what you have studied, right? Okay. But just with a pinch of salt, I think you can say that this is definitely going to be much, much better than 0.7 degree accuracy. Okay. And by the way, this 6 degree number, right? Okay, which I came up with, right? It's not like some random number I'm choosing here. It's really how most ADCs and DACs and their phase noise is somewhere between this kind of property. Okay. Anyways, you don't need to know this kind of detail, but just understand that these numbers are coming from some realistic hardware. Okay, and not just something I'm making up as I go. Okay. And the point I want to convey is that really with this kind of averaging, right? Okay, I can get to 0.7 degree accuracy. Okay, and I even got to 60 hertz, right? Okay, or if I go to 3 hertz, right, I would get further more accurate phase measurement. Okay, but then what would happen if I go to 3 hertz? Okay, sorry, let me just, I'm trying to find, okay, let me just rewrite all these things. Okay, so we got to the accuracy of phase measurement. Okay, so there is accuracy, right? Okay. So the more I average, okay, accuracy is dependent upon averaging, okay, right? The more I average, the lower the sampling rate will be, okay, correct? Increased averaging decreases the sampling rate, okay? What does decreased sampling rate have an effect on?
Frequency resolution.
Yep, perfect. Everyone follows Puneet's thought, Dylan?
I didn't
Remember,
quite catch that.
yes, so let me explain, right? So what happens if you sample, let's take d of t, okay, right? This is your d of t, okay, right? Okay, we studied that we can take Fourier of it, right? Okay, and we'll get 1 on the DC subcarrier, we'll get d0, right? Correct, Puneet? Sorry, Dylan. And at zero point 0.2 hertz, we'll get breathing, right? Okay, this is d0, breathing, right? And at somewhere between 1 hertz, I don't remember exactly if we called 1 hertz, right? Let's say it's 1 hertz, okay? We'll get DH, okay? Right? Right? Eric, oh, sorry, Dylan rather.
Yeah.
Okay. So now if I do 60 hertz of sampling of this thing, okay? Right? Okay. What does this mean? This means this frequency is 0, right? Okay. All right. And what else? What is the bin separation here, Dylan? let's say I have these samples, right? Okay. So this is 60 hertz, correct, Dylan?
The separation would be 1/60.
Yep. Following me? Oh no, sorry. What am I saying?
It would
Sorry, my
depend
bad.
on number of samples, right?
Yeah, it would depend upon number of samples. Sorry. Yeah, I think 1/60 is something here rather. My bad. What am I? This is 1/60, right? This is 60 over n. Okay, right? But let's understand this part. Okay, so let's take we have 10 breathings. Okay, or the whole point is that in order to measure breathing and heart rate, right? Okay, you only needed, let's take an example of n, right? What n should we take? Let's take 1200, okay, like last time, okay, which is equivalent to how many samples, Dylan? 20-second worth of samples, right? Correct?
Yeah.
So this basically what sampling rate plays into is trying to have more bins in between this, right? The separation will be 60 over n, right? Which is essentially 60 over 1200, let's say in this case, right? And that will give you somewhere between 1/20, which is 0.05, okay? It will give you 4 bin separation between this DC and the first breathing, and then even good enough separation in between these two, okay? So it's slightly indirectly related, okay? And the more, once you do your assignment, you guys will also figure out these things, right? So increasing sample rate, okay, let's say if we take, instead of 60, if we went to 120 hertz, okay, what would happen here? Okay, same amount of time of 20 seconds, okay, 20 seconds will generate how many samples? 2400 samples, right? Correct?
100.
Right. Sorry.
My bad. Go ahead. Sorry.
So everyone following with me so far? Questions, thoughts? Okay. So now we understand sampling rate, accuracy, right? Okay. And this accuracy is important to make sure you get DH and DB, because DB is on the order of tens of centimeter. This is on the order of 0.4 millimeters. Okay, right? So this comes to your accuracy, the smaller magnitudes of these signals. Okay, right? And how the noise and averaging of the noise kind of plays into this. Okay, right? So we have covered sampling rate, we have covered accuracy, right? What was the third thing? I forget. That was third thing. Wavelength. Okay, all right. So lambda. Okay, wavelength. Okay, and it turns out to be 1.5 gigahertz. Okay, right. Now, hopefully, this explains everyone uh, what how to analyze this overall system. Okay, I think I'm going to take a little bit of a detour here. Okay, and really strengthen your. So, tell me what's the problem with this current system we have designed. Okay, what do you guys feel about the system's performance? Right, it's too fragile, right? Okay, it's like very carefully designed that we don't go over one wavelength, right? Okay, like distance d, right? Okay, here it has to be between 0 to lambda by 2, right? Okay, and then the phase accuracy is also needs to be something like this, right, on this y-axis, and the sampling rate and all these things needs to be chosen very carefully, right? Okay, so it's a very fragile in some ways, right? Okay, does that make sense to everyone, how it's fragile? Eric and Dylan, following me so far?
Yeah, I'm
I'm still
following.
following.
Good, thank you. So I think idea and observation is following. Okay, in the next class we'll go to multiple wavelength and we'll think about that as an overall problem statement. Okay, right. Today I want to just strengthen one other topic right now. Okay, which is essentially FFTs. Okay, simple FFTs. Okay, and then let me just take a little bit of slight detour. Okay, right. Okay, so we'll start with physical processes and then understand range, resolution, and aliasing kind of things. Okay. So let's start with the physical process. Right? What is the physical process? The physical process is D of T. Okay. Right. Sorry, this is rather T is here the time. Right. And D is what the y-axis is. Okay. Right. A true delta function of this, if this is like continuous, then we do DTFT, right? Sorry, not DTFT. What am I saying? Fourier transform. Let's call it Fourier transform. Okay. This Fourier transform leads to zero. It leads to zero, right? And this leads to, let's say, a delta function in frequency domain at FP and FH. Okay, right? So this is like the true nature. Okay, nothing diluted, nothing concretely corrupted in any ways. Okay, right? Okay. So now, what happens to this process, right? When I only look for a short period of time. Okay, right? Okay. I look for it from 0 to, let's say, some T naught time. Okay. What happens to this process? This was infinite time, by the way, first process. Okay, here what we will measure. Okay, Dylan, what happens to this when you only observe for a short period of time? This comes from your like DSP, but I'm planning to cover it. But go ahead, yeah, Dylan. Yeah.
That your spectrum becomes periodic.
Okay, that's good. Okay, not yet there. How about Eric?
It's been a little while for me, so I've forgotten.
That's okay. So look, you're windowing in time. Okay, so let's do more simpler thing here. Okay, let me erase this a little bit. Right. Okay. Let's assume this is infinite time process which you're seeing on the top. Okay, right. What I'm going to do is I'm going to multiply it with a rectangular of 0 to T naught. Okay. So what is the rectangular's Fourier transform? It's sinc.
Sync function.
Yep. Thank you. So this basically becomes with 1 over 2 T naught or T naught. I don't remember this exact part, right? Okay. Right. So this is what the Fourier transform of this, right? Okay. Now, if you multiply this with this, okay, what happens when you multiply something in time domain? Eric?
You'll convolve the two of them in the frequency domain.
Yeah. So you'll convolve here, okay, right? So let's say I take this process now, okay, okay, up to time T naught, right? Okay. What ends up happening is that you will have this delta function which gets convolved with this sync. The FP's delta function also get convolved with the another sync, and FH's delta function gets also convolved with another sync, right? Correct? Everyone following me? There are 3 delta functions. Each of them will get convolved with sync, right? So what that happens is that there will be a sync on top of the delta function, each delta function, right? Is that clear to everyone? Eric, Dylan?
Yes.
Yeah.
Okay. because basically you just kind of take this sink and put on top of each other, right? That's what the delta function convolution leads to, right? Correct. Now, again, you can't even do real world, like you can't do infinite samples, right? Okay. This is also an abstraction, right? What I mean by that is that in order to get this kind of signal, right? Okay. There is no way we can measure analog signals, right? In real world, you only can measure or sample this signal at finite number of points. Okay. What I mean by that is that you can find sample at this signal at some points. Okay. Right. Okay. Correct. Right. And that's what we did in the one I just explained you guys earlier. Okay. So continuing with this thought process. Okay. What happens when you sample something? Now, Dylan, you want to try again answering this question?
Yeah, it's like a infinite pulse train.
Yes. So that's a good answer. Okay. Let me now show exactly what Dylan meant. Okay. So what we are going to do is we're going to just have an impulse train here now. Okay. And let's say this is a TS 0, 2 TS, right? What is the impulse do? What is impulse train's Fourier transform?
Like a white noise.
Is it? It's
No,
impulse
sorry,
train.
it's another impulse train.
Dylan, Eric, following? Puneet? Sorry,
It's an
couldn't hear you, Eric. Sorry.
Oh, I just said yes, Paul.
Yep. So impulse trains is also impulse train. Okay, but the only thing is that the difference or the separation between these two impulse train is given by 1 over TS. Okay, right. So now let's just put this in this context today. What we discussed, right? Our sampling rate TS, for example, was 3 gigasample. Okay, right. Okay. So that means that in this time domain, it was 1 over 3 gigasample is the separation between these two. But in this, it's essentially 3 gigahertz of difference between these two, right? Okay, right. Similarly, we can take 60 hertz. Okay, if this were 1 over 60 hertz, okay, this would have been 60 hertz. Okay, right. And look at the process we are actually trying to measure. This process is 0.2 hertz. This process is, let's say, 1 hertz somewhere. Okay, right. So really, really far away, they will be repeated. Okay, all right. Following, Eric, Dylan. So let me just do now following. Okay, now what am I going to do? I'm going to take this signal and multiply with this in time domain. Okay, what would that lead to? Convolution here. Okay, following, guys. Eric, Dylan, Puneet.
Yeah, I'm following.
yes.
Okay, so I'm going to multiply these two. Okay, right, and I get this. Let's say small sample things, right? Okay, you follow me basically, right? Okay, I get these samples of, okay, right? And what these samples are doing really is, now let me just try to be as good as at my drawing, right? I will basically have a sink because of D0, first this one, then I will have an FP sink. Okay, just gonna rewrite it, FP sink 0 and FH sink. Okay, and then same, I will have here another D0 related but sink, but at D0 plus 3 gigahertz. Okay, everyone following on this one? Let's call it, this is 0 plus 3 gigahertz for this particular repetition. Okay, depending upon if it is 3 gigahertz. Okay, okay. Sorry, yeah, it's almost out of the board, but gigahertz. Okay. And then same thing, there will be breathing one at FB plus 3 gigahertz. Okay, right? Everyone with me on this at part? Dylan, Eric, Neat?
Yeah.
Okay, all right. Okay, I'm just drawing it up so that there's a clear on this part. So now this is what your ADC samples look like. Okay, right? Okay. So now tell me what happens when you take FFTs in your MATLAB, right? What exactly do you do? Anyone answering this question will get an extra just bonus point to think about this. What are FFTs, by the way? So let's see, right? Let's go back. This is, let's say T naught is your 20 seconds, okay, right? And basically you will take T naught up to 20 seconds of samples, okay, right? Now, and for this example, let's take sampling rate TS, okay, 1 over 60 hertz, okay, right? All right. So now in total, I have 1200 samples in this case, correct? Right? Okay. Instead of 3, with this, I will have this at 60 hertz plus 0. Okay. Everyone with me on this so far? Okay. What happens when you do FFTs? Okay. First of all, not just the time domain samples are discrete, right? Even the output here you have at FFTs is also discrete, right? Okay. How many points you get when you take 1200 points FFT? You get 1200 points. Okay, correct? Correct, everyone?
Yes.
Yeah.
So how should I interpret it, right? So now let me give you one more final example in this, right? Okay, there is another impulse train, okay, and that will lead to your FFT, okay? So what that impulse train is following. What we are going to do is really in frequency domain, okay, I'm gonna multiply with the following, okay? So the separation between these two samples is 60 hertz divided by total number of samples, which are 200 samples, let's say, okay? Right, okay? So this is your 0, this is 60 upon whatever this number is, right? Okay, and this is, it's an impulse train here, okay? Right, everyone with me? Up to, all the way up to minus infinity to plus infinity, okay? The separation between these two bins is 60 hertz over 1200, okay? Roughly said it's 0.05, okay? Right? Everyone following? This is an impulse train here, okay? What I'm going to do is I'm going to multiply in this domain, okay? That leads to convolution with, what happens with this kind of impulse train, guys, okay? Here, what will be that time domain response look of this impulse train? Puneet?
It will be an impulse trend, like
It will be an impulse train. It will be repeated after 1200 samples
1200
or
samples.
the other 20 seconds here, okay? Dylan, following me? Eric?
Yeah, I'm following.
Sorry, someone was not able to follow. Eric?
No, I get it.
Good, good. And if it is too simple and too obvious, just let me also know that, okay? Because I've been trying to slowly ramp up, okay? But so basically, you get this, and there will be an impulse train at minus 20, okay? Let me draw a dot and say this is at minus 20 seconds, which is minus 1200. So basically, what happens is that the time domain signal is getting convolved, right, with this kind of impulse train. What would look like in time domain? What would happen? The output of this will be Anyone want to take a shot?
You would get the periodic extension of this signal that you originally sampled over that 20 seconds.
Yes. We'll get 0 to 20-second signal, what you have actual signal, okay, sampled again, all right. And its same copy will be repeated after 20 seconds, okay, right, okay. This is your time domain, okay, all right, okay. Now let's draw a frequency domain in the second line here, okay, right. In frequency domain, we are multiplying, okay, okay. What that gives you is really, it will give you a sync function basically sampled at these points, okay. We'll essentially have this sync function sampled at different points here, okay. Let me use a different color so that it's clearer. Will be sampled at different points here, okay. Everyone with me on this? So I get a sample. Let me draw this in the nicest possible way I can, okay. Okay. So this is what I get here, right? Okay. You can call it 0 to how far away it will be, up to 60 hertz, okay, right? And how many points you will have? You'll have up to 1200 points here, okay? Everyone with me? And what would happen after 60 hertz, or here for that matter, okay? After 60 hertz, let's say you will essentially have a repetition of exactly what this was here, okay, right? Following Eric and Dylan, Puneet?
Mhm.
Yes.
Yeah.
So what FFTs are this, okay? It's essentially something which is periodically repeated in time and periodically repeated in frequency, okay? And what really that gives you is ability to think of them in a different ways, okay? And what I mean by that is following, okay? So I can think from, instead of 0 to 60, I can think of 0 to plus 30 and minus 30 to plus 30, okay? I can take this transform to look from minus 30 to plus 30, okay? Instead of looking from 0 to 60, okay? And this is what probably I think Ish covered in your lab as well, right? This is FFT shifting this, okay? Right? And FFT shifted versions are what typically people tend to look and try to get it, because if you are working with real signals, right? Okay, then they will create an image copy as well, okay, right? And probably you might have seen that in the lab, right? Correct, everyone? Puneet? Sorry, did you say something, Puneet? I didn't hear.
Yeah,
Okay, good.
it's
So
like we covered this in the.
yeah, so basically you get repetitions in negative axis, right? So typically people tend to consider minus 30 to plus 30 as the appropriate domain to look at these things, okay, right? So now let's go back to range and resolution questions we have been asking about, okay, right? So typically what I tend to do when I say if things are separable or not, right, okay, and you can apply here some engineering approximation. It's not like a golden rule, okay? So the point is following, okay? True nature process is separated by this much amount, okay? True nature process is separated by this much amount, right? Everyone seeing my pointer, right? And when I say I want to separate them out, right, and make sure that they are separated well enough, right, okay? Typically what I tend to mean is that they should be separated at least by one sample, right? This delta function and this delta function should have one sample in between them. Okay, right? Okay, and this is where all of your range and resolution will come out. Okay, so now let's go over this example to just quickly nail it down. Okay, here, right? Okay, if this time domain, okay, if the process occurred at time 0 or at time delta, okay, let's say some event occurred at time delta here, okay, versus some event occurred at 20 plus delta, okay, right? Okay, they will look the same. Everyone following? Because it's like periodically repeated, right? It will be copied over here, okay. Eric, Dylan, following?
Yeah, I'm following.
This is called as aliasing, okay, right? Imagine all of this signal, right? All of this signal, right? Instead of happening in 0 to T0, it could have occurred in T0 to T0, okay? But it would create the same time domain, same FFT, same everything, okay? Right? That's aliasing, right? Which is T0. Anything plus minus K T0, right? Kind of can be considered as aliasing, okay? Right? Okay. Now, how about resolution? What is resolution, right? What are the two processes I can separate here? Okay, ignoring the sync part. Okay, right? Truly ignoring the sync part, the two processes I can separate are T naught over. Come on, folks. Sorry. Let's start from simple observation, right? Okay. So let's bring down it's 60 hertz observed at 200 to 1200 samples, correct? The total frequency axis was 60 hertz, okay? And I have 1200 point division, right? So I get 0.05 hertz, okay? Right? This is to say the resolution is 1 over T naught,
T0.
okay? Everyone with me? Dylan, following?
Yeah, I'm with you.
Okay, good. So we understand resolution and aliasing, okay? Right? And hopefully now the Nyquist concepts and everything else makes very clear sense for everyone, okay? Questions? So next class, okay, this title should be cut off for this. This was FFT continue, okay? Next class we'll go over multiple wavelength, okay, and how you can think of this system when you have multiple wavelength, okay? All right, and that's really how we can make it more robust. And then we'll slowly transcend into FMCW with multiple wavelengths, okay? And the next lab will be potentially about how basically FMCWs and multiple wavelength systems should be thought about, okay? And starting to trying to analyze breathing and heart rate from that, okay? All right, questions?
In this system, we are still considering the object is stationary. The person whose heartbeat we are measuring is stationary.
Yes, yes. So that's exactly why the system is super fragile, okay? So again, and so just to give you context, right? When you move, right, typically the speed of your movement is considered. So motion is quite often interferes with your breathing and heart rate. Okay? It comes very close to the rate at which you typically breathe and have a heart rate. Your movements are also very close to it. Okay, so they will interfere, right? Okay. Right now we are still assuming it's stationary, right? And we will assume the persons to be stationary all the way up to week 4 or week 5 until we start looking at multipath and dynamic multipath. Okay.
Okay.
First, we'll all build up the FMCW system and see how we can get breathing and heart rate with wireless signals. Okay.
Entirely, like we'll always assume the system is synchronized, like TX and RX are always synchronized, or there will be.
Or you can do unsynchronized analysis. Okay. The issue with unsynchronized is that that doesn't occur in nature. Quite often, if you have these systems, right, because transmitter and receiver are co-located, right,
Yeah.
it doesn't make sense to consider them not synchronized. Okay, so there can be some calibration which you need to do. Okay,
Okay. Okay.
but once you do those initial calibration, the synchronization of the system can be assumed very nicely, right here, for example.
Yeah. Okay.
The screen share is not coming up somehow. Okay. Can you guys see
It's
the?
showing. It's showing.
Okay,
Yeah,
I don't know. Some
we can see
screen
the
is- yeah. Are you seeing the transmitter and receiver, or you're seeing the
multi-wavelength based system.
No, it's not showing the right screen then. Anyways, continue. Yeah, you get the point, right?
Yeah,
You may but
I get the
beyond that, I don't think anything else.
Okay.
Okay. Right. I'm gonna stop recording. Meanwhile, if you can have questions, please feel free to continue. Right. Okay.